Hi everyone, today's video is about elementary matrices. Elementary matrices represent a dictionary between elementary row operations, which we've used for Gaussian elimination to solve linear system, and the matrix language that we have been developing. In fact, here's the definition. An elementary matrix is a matrix that we get by performing any single elementary row operation to the identity matrix In. Here's a little example. This is an elementary matrix because it can be obtained from an identity matrix 3 by 3 by replacing the first row with a copy of the first row plus twice the second row. And that's what we get here, 1, 2, 0. The consequence of this definition is that we have an exact correspondence between row operations on one side and elementary matrices on the other side. Here's a few examples. There's E1, the matrix that we just saw. It corresponds exactly to the elementary row operation R1 plus 2R2, adding twice the second row to the first. Here's another elementary matrix. You see that this comes from an identity matrix where the first and second row have been switched out. So that's the corresponding row operation. And as another example, this E3 is a matrix obtained by from the identity by multiplying the third row by 4. And that's exactly the corresponding operation. The crucial fact about elementary matrices is that if I give you any matrix A, given any matrix A, performing a row operation on A is the same as multiplying A by the corresponding elementary matrix. In other words, well, we'll see it in examples here. Let's have a look at this first example. I get a generic matrix A with entries A, B, C, D, E, F, G, H, I. Performing the row operation, replace the first row by itself plus twice the second, on the matrix A looks like this. You see I have the first row plus twice the second, 2D, 2E, 2F. But in fact, if I were to multiply my matrix E1, which corresponds to that operation, the result would be as follows. Well, in the first entry here, I would have 1 times A plus 2 times D plus 0 times G. So that's A plus 2D. The second entry here would be 1 times B plus 2 times E plus 0 times H. The third entry would be 1 times C plus 2 times F plus 0 times I. And now let's have a look at the others. The second row, when I look at the second row of the matrix, this is a typo, should be 1. When I look at the second row of E1, that's 0, 1, 0. So this will extract exactly the second component of every column, D, E, F, and then I encourage you to finish up the computation, and you'll see that you get G, H, and I. The crucial part here, this is 2F, is that you get exactly the matrix you would get by performing a row operation. Let's try to do it with another example. When I get E2, switching the rows would have the following effect on the matrix A. This is D, E, F, A, B, C, G, H, I. Let's try to multiply A to the left by the matrix E2. I'll compute the first row. It's 0 times A, 1 times D plus 0 times G. 0 times B plus 1 times E plus 0 times H. 0 times C plus 1 times F plus 0 times I. And I get F. The second row, 1 times A, 0, 0. 1 times B, 0, 0. 1 times C, 0, 0. The third row will also result in GHI. And you see that the result is the same. Performing the row operation is the same as multiplying by the corresponding elementary matrix on the left. Here's a last example. Maybe let's compute yeah, let's just compute the third row because that's when something is going to happen. Check by yourselves that the first two rows of this product will remain the same, but for the third, I will get something like 0 times A plus 0 times D plus 4 times G. Likewise, I will get 4H and 4I by multiplying it out. Similarly, if I were to apply the elementary row operation, which replaces the third row by 4 times itself, I'll get 4G, 4H, 4I. This is important consequences. The most immediate one is that every elementary matrix must be invertible because every row operation can be undone. So if I can undo the row operation, then I must be able to undo the corresponding matrix. And in fact, not only are elementary matrices invertible, but we already know the inverses because the inverses will correspond to the inverse elementary row operation. Let's have a look at this example here. My row operation replace first row with itself plus twice the second gives me my matrix E1 from our example. But then to get back to the identity, I will apply the inverse operation, which is subtract twice the second row from the first, and that gives me the identity. So this operation here will correspond to a matrix E1 inverse. And in fact, the row operation R1 minus 2R2, if you apply that to the matrix, through the identity matrix, you get the elementary modification, but the elementary transformation, elementary matrix E2 that looks like this. Let's check that these matrices E1 and E2 are inverses from one another. Well, to check that they're inverses, I need to apply E2 to E1, but multiplying E1 by E2 on the left is the same as applying the transformation R1 minus 2R2 to E1. If I do that, this is my matrix E1. I subtract twice the second row from the first, I get exactly the identity. Let's try to check the other order as well. Multiplying E2 by E1 on the left is the same as doing the operation R1 plus 2, R2, and replacing R1 with that. So if we do that with E2, I do this operation here to the matrix E2, what I get is I eliminate the minus 2. And I get the identity. So indeed, elementary matrices are all invertible, and the inverses are the inverse operation. Let's wrap up what we've seen in this example in the following theorem. If I give you a matrix whose reduced row echelon form is R, then the theorem says that there exists an invertible matrix such that, well, there exists a matrix P such that I can get to the reduced echelon form by multiplying A by P on the left. How does that work? The reason why that's true is that I can get to the reduced row echelon form by applying row operations. I'll call them row 1, row 2, and so on. Sorry, R1, R2, and so on. So I start from my matrix A, and then I apply a row operation. I get another matrix A1. I apply another row operation, and so on until I get to some amount of row operations, and I get to my reduced row echelon form. But now, all of these row operations correspond to elementary matrices. And we know from what we've been discussing, for example, is that A1 is nothing but A multiplied by E1, the elementary matrix associated with R1. So A2 will be A1 times E2. But A1 is E1 times A, so this would be E2, E1, A. What I want to get to is the following equality. I can get to R by starting from A and then multiplying by E1, and then E2, E3, all the way up to En. I collect all these matrices into a bunch, this product of matrices, and I call that P. And that's the P in the theorem. Furthermore, P has a very nice property. It's a product of invertible matrices. So P is an invertible matrix. What this means is that if the reduced row echelon form of A is the identity, then A is also invertible, and P is its inverse. Let's think about this for a second. So in this other theorem, we are assuming, if we assume that A has the identity as a row echelon form, then by the previous theorem, we have that there exists a matrix P, product of elementary matrices, such that P times A is the identity. Now, P is invertible because it's a product of invertible matrices. And products of invertible matrices are invertible. Meaning that if I take this equality here and I multiply both sides by P inverse, I get that A, well, let's do all the steps. I get P inverse PA is equal to P inverse times the identity, which simplifies to A equals to P inverse. But now, if A is equal to P inverse, A is the inverse of an invertible matrix. That means by the property of invertible matrices that A is invertible as well, and its inverse is exactly P. So that's what the content of this theorem is. What we'll see in the next video are some consequences of the existence of such a matrix P. It will have profound impact on the theory as we are developing it right now.